A planet the size of Jupiter is bleeding helium into space right now. The trail stretches 10 times its own radius, and it rains sand there. The James Webb Space Telescope just captured this for the first time. In the next 8 minutes, you will see how this discovery connects to Venus, reveals planetary migration, and changes what we know about atmospheric escape. The planet is WASP-107B. It sits 210 light-years from Earth. JWST detected something astronomers had never seen before with this telescope. Massive clouds of helium gas streaming away from the planet. This marks the first time helium has been identified by JWST on an exoplanet. The detection came on the 23rd of June 2023. JWST's near-spec instrument observed for 6.5 hours. The signal was powerful. The transit depth reached 2.395%, plus or minus 0.01%. The detection significance hit 36 sigma. That is not a marginal result. That is definitive. But here is where the physics becomes striking. The helium absorption starts 1.5 hours before the planet crosses in front of its star. The gas cloud blocks starlight before the planet itself arrives. Think about what that means. The atmosphere extends so far that it precedes the solid body by a significant time margin. WASP-107B was discovered in 2017. Astronomers immediately recognized it as unusual. The planet measures roughly Jupiter's size, but it contains only 1/10 of Jupiter's mass. This places it in a category called superpuffs. These are exoplanets with extremely low densities. WASP-107B orbits 7 times closer to its star than Mercury orbits our Sun. At that distance, the stellar radiation heats the atmosphere to extreme temperatures. The atmospheric escape models confirm helium flows both ahead of and behind the planet. The flows extend in the direction of orbital motion. They reach nearly 10 times the planet's radius. Jan Carteret, a doctoral student in the Department of Astronomy at the University of Geneva and co-author of the study, stated, "Our models show the presence of helium streams extending to approximately 10 planetary radii. The thermosphere stretches to dozens of planetary radii. This is the extended upper atmosphere called the exosphere. Gas particles move so fast at these altitudes that they overcome gravity. They escape into space permanently. Now the chemistry reveals the planet's history. JWST detected water vapor in the atmosphere. It found carbon monoxide, carbon dioxide, and ammonia. It also detected sulfur dioxide. But methane is absent. JWST can detect methane easily. Its absence tells us something specific about conditions and formation history. The atmosphere also contains clouds, not water clouds, silicate clouds. These are tiny particles of sand-like material. The temperature is high enough that silicates vaporize on the day side. They rise into the upper atmosphere. As they circulate to the cooler night side, they condense. Then they fall as sand rain. The cycle repeats continuously. This silicate weather system shapes the atmospheric structure. The metallicity of the atmosphere measures 30 times solar values. That number is a clue. Planets that form far from their stars typically have higher metallicity. They accumulate more heavy elements during formation in the cold outer regions of protoplanetary disks. WASP-107B likely formed much farther out than its current position. Then it migrated inward over time. The migration would compress the atmosphere and trigger enhanced gas loss. This explains the bloated structure and ongoing helium escape. Thank you for being with us. Please subscribe, share, and... The study also detected stellar spots on the host star. The signal reached 5.2 sigma. Stellar spots are cooler regions on the star's surface. They affect the light curve during transits. The spots complicate the measurements, but the team accounted for them in the models. The helium signal remains robust even after correcting for stellar activity. WASP-107B is only the second exoplanet with a complete JWST spectrum covering 0.6 to 12 micrometers. This full wavelength coverage comes from combining multiple instruments. It provides a comprehensive view of atmospheric composition. The potassium upper limit sits at log base 10 of less than -4.86. That extremely low abundance suggests specific chemical pathways dominate. Vincent Bourrier, senior lecturer and research fellow in the Department of Astronomy at the University of Geneva and co-author of the study, stated, "Observing and modeling atmospheric escape is a major research area because it is thought to be responsible for characteristics observed in the exoplanet population. Atmospheric escape is not unique to exoplanets. Earth loses atmosphere too. Our planet sheds a little more than 3 kilograms of matter every second. Most of it is hydrogen. At Earth's distance from the Sun, this rate is too weak to drastically alter our planet over billions of years. But for planets closer to their stars, the process accelerates dramatically. Venus offers a cautionary tale. Venus likely had water early in its history. Atmospheric escape models suggest that intense solar radiation drove hydrogen from water molecules into space. Oxygen either escaped or bonded with surface rocks. Over geological time, Venus lost its water. What remains is a thick carbon dioxide atmosphere with crushing surface pressure. Atmospheric escape shaped the planet we see today. The same process affects rocky exoplanets close to their stars. If a planet orbits too near, stellar radiation can strip away its atmosphere entirely. This may explain why we observe a radius gap in exoplanet populations. Planets between 1.5 and 2 Earth radii are less common than expected. Atmospheric escape could erode the envelopes of small Neptune-like planets, leaving behind bare rocky cores. Over time, the population splits into 2 groups: small rocky worlds and larger gas-retaining planets. WASP-107B provides a laboratory for studying these processes in action. The helium detection is crucial because helium traces atmospheric structure. Helium is chemically inert. It does not react with other elements. It escapes based purely on temperature and gravity. By measuring helium, astronomers map how energy from the star flows through the atmosphere and drives gas loss. The observations also reveal stellar complexity. The host star's activity affects the measurements. Spots rotate in and out of view. They modulate the light. Separating planetary signals from stellar signals requires careful analysis. The team used tools developed at the University of Geneva specifically for this purpose. The models successfully isolated the helium signature despite stellar contamination. The international collaboration included scientists from the University of Geneva, McGill University, the University of Chicago, and the University of Montreal. The team combined observational data with sophisticated atmospheric models. The models simulate how radiation heats the upper atmosphere and accelerates particles to escape velocity. They predict the spatial distribution of escaping gas. The predictions match the observations closely. The study represents a key reference for understanding planetary evolution. It shows that atmospheric escape shapes not just individual planets, but entire planetary populations. The characteristics we observe today result from billions of years of gas loss. Some planets retain thick atmospheres. Others are stripped nearly bare. The outcome depends on stellar distance, planetary mass, and atmospheric composition. The implications extend beyond WASP-107B. Thousands of exoplanets have been discovered. Many orbit close to their stars. Understanding how their atmospheres evolve helps us predict which planets might retain conditions suitable for life. Rocky planets in habitable zones need atmospheres to maintain liquid water. If escape rates are too high, the atmosphere vanishes. The planet becomes uninhabitable. JWST continues to observe exoplanets across a range of sizes and orbits. Each observation adds detail to our understanding. The helium detection on WASP-107B opens new possibilities. Future studies will search for helium on other planets. They will map how escape rates vary with stellar type and planetary mass. The data will refine models of planetary evolution. The sand rain on WASP-107B also deserves attention. Silicate clouds affect how much starlight reaches lower atmospheric layers. They alter the temperature structure. They may influence escape rates indirectly. Understanding these complex interactions requires combining chemistry, thermodynamics, and fluid dynamics. JWST provides the observational constraints. Theorists build the models. Together, they reveal how distant worlds work. We are witnessing planetary evolution in real time. WASP-107B is losing mass. Its atmosphere thins gradually. Millions of years from now, it may look completely different. The helium tail we see today records a snapshot of that transformation. The planet will continue migrating or stabilize in its current orbit. Either way, its structure will change. The connection to our solar system matters. Understanding atmospheric escape on exoplanets informs our knowledge of Venus, Mars, and Earth. It places our planets in a broader context. We see that atmospheric loss is a fundamental process shaping planetary outcomes across the galaxy. Thank you for being with us. Please subscribe, share, and like.